Most of rotation has been an application of concepts we saw earlier in the semester in a different way. However, the law of conservation of angular momentum is something new. It is the punchline to our entire discussion of rotation. In an earlier video, we defined momentum as mass times velocity. It is a vector, and it is useful in solving collision problems. Angular momentum has an analogous definition: moment of inertia times angular velocity. Angular momentum is symbolized with the capital letter L and is measured in kilogram meters squared per second. It is a vector quantity as well. Just like angular velocity, we will use the convention that an object rotating counterclockwise has positive angular momentum, and an object rotating clockwise has a negative angular momentum. Your book discusses many interesting connections between angular momentum, linear momentum, and torque. In the interest of time, we will just look at how to solve puzzles using conservation of angular momentum. The law of conservation of angular momentum says that if you have several rotating objects, their total angular momentum before they collide must equal their total angular momentum after they collide. It also says that when the moment of inertia of an object decreases, its angular velocity must increase and vice versa. This is most famously seen in figure skaters. They decrease their moment of inertia by drawing in their arms, and as they do so, they spin faster and faster. Let's see some examples. Here we see a carousel with a radius of 3 meters and a mass of 50 kilograms. It is standing still. A 10-kilogram dog runs around it in a circle at a speed of 2 meters per second and then jumps onto the rim. How fast does the carousel rotate? We have to compare the overall angular momentum of the dog and the carousel a nanosecond before they made contact to their angular momentum a nanosecond after the dog landed. The dog was running around the outside rim of the carousel at 2 meters a second. We can calculate its angular velocity by dividing v by r. That gives us an angular velocity of 0.66 radians per second, and since the motion was counterclockwise, we consider this as being positive. We can treat the dog as a particle. Its moment of inertia is given by mr squared. That works out to 90 kilogram meters squared. We can also work out the moment of inertia for the carousel. We can treat the carousel as a cylinder. Its moment of inertia is given by 1/2 mr squared. That works out to 225 kilogram meters squared. Now, let's apply all this information to conservation of angular momentum. The total momentum before the collision equals the total momentum after. We can expand out the total momentum to account for the individual momenta of the dog and the carousel, and then we can expand those to account for the definition of angular momentum. We can substitute in all we know. Originally, the carousel was standing still, so its angular velocity at the beginning is 0. When the dog jumps on, it remains at its original distance from the center, that's 3 meters, so its moment of inertia hasn't changed. The other thing is, after the dog jumps on, it spins at the same rate as the carousel. So the angular velocity of the dog after it jumps on equals the angular velocity of the carousel. We can therefore solve for the final angular velocity of the dog and the carousel. It works out to 0.19 radians per second. Suppose the dog is at the rim of the carousel. Remember, the dog is 10 kilograms and the radius is 3 meters. And the carousel is rotating at 5 radians per second. The dog then jumps off, landing at rest. What is the angular velocity of the carousel after the dog jumps off? The rotational inertia of the dog is the same as it was in the earlier puzzle, 90 kilogram meters squared. In fact, it would stay the same as long as the dog stays 3 meters from the center. Since the dog ends up at rest, its final angular velocity is 0. We can plug in all the known information, and then we can solve for the final angular velocity of the carousel. It is 7 radians per second. It's positive, which means the carousel continues rotating counterclockwise. Suppose the dog is back on the rim of the carousel and both are initially at rest. Then the dog starts running around the rim at -8 radians per second, that is, clockwise. How does the carousel respond? Again, we can plug in all the known information into conservation of angular momentum. The initial angular velocities of both the dog and the carousel are 0, and it's easy to solve for the final angular momentum of the carousel. It is 2.4 radians per second, which is counterclockwise. Here, we see a 500 kilogram spacecraft in an elliptical orbit around the Earth. At its closest approach, it moves at a speed of 1,000 meters per second. If its closest point is 10 to the power of 7 meters from the center of the Earth, and the furthest point is 5 times 10 to the power of 7 meters from the center of the Earth, what is its angular velocity at the furthest point? Well, we first need to convert the linear velocity into an angular velocity. We do this by taking the linear velocity and dividing by the radius to get the angular velocity. Next, we determine the moment of inertia of the spacecraft at its closest and furthest points. We can treat the spacecraft as a particle, so its moment of inertia is mr squared. The moment of inertia at the closest point is 5 times 10 to the power of 16 kilogram meters squared, and its moment of inertia at the furthest point is 1.25 times 10 to the power of 18 kilogram meters squared. Just like the figure skater, the moment of inertia of the satellite changes. We can now apply this in conservation of angular momentum. At its furthest point, we can solve that the magnitude of angular velocity is 4 times 10 to the power of -5 radians per second. Now we will change tack and talk about rotational kinetic energy. Rotational kinetic energy works a lot like linear kinetic energy. The formula for rotational kinetic energy is 1/2 I omega squared, which you'll notice is analogous to the equation for linear KE. Rotational KE can be used in conservation of energy just like linear KE. In fact, it's also measured in joules. The two frequently occur at the same time. We will see this in 2 examples. Here, we see a bucket being lowered over a pulley wheel. The bucket has a mass of 2 kilograms and is initially at a height of 4 meters and not moving. The wheel has a mass of 10 kilograms and a radius of 0.2 meters. As the bucket descends, the wheel turns. The rope does not slip on the wheel. What is the velocity of the bucket when it hits the surface of the water? First, we need to find the moment of inertia of the wheel. That's 1/2 mass of the wheel radius of the wheel squared, or 0.2 kilogram meters squared. Initially, the bucket has gravitational potential energy. By the end, that potential energy due to gravity has turned into 2 forms of energy: the linear kinetic energy of the bucket and the rotational kinetic energy of the wheel. The rope does not slip on the wheel. That means the linear velocity of the rope equals the linear velocity of the rim of the wheel. But the linear velocity of the rim in turn equals radius times angular velocity. So we substitute that in this last equation. This gives us an equation that contains only the velocity of the falling bucket, so we can solve for this velocity. Solving, we get 4.74 meters per second. That is the speed of the falling bucket. This is less than it would have been had some of the potential energy not gone into turning the wheel. I won't go into the calculation, but had the wheel not been there, the bucket would be moving at close to 9 meters per second. A related puzzle is an object rolling down a ramp. Here, we see different objects rolling down a ramp from an initial height of 1.5 meters. Rolling is a motion that combines linear and rotational motion. Notice that the objects all have different accelerations. That's because even if they have the same mass and radius, they still have different shapes and therefore different moments of inertia. Let's focus on the sphere. It has a mass of 20 kilograms and a radius of 0.5 meters. Like before, we solve for its moment of inertia, 2 kilogram meters squared. And like before, its initial potential energy gets turned into linear kinetic energy and rotational kinetic energy. The only difference is the two forms of energy are now present in the same object. Since the object rolls without slipping, the angular velocity is v over r, and we can substitute that in. And so we solve for the linear velocity of the sphere in a very similar way to how we did before. The linear velocity of the sphere, once it reaches the bottom, has a magnitude of 1.69 meters per second. In this video, we discussed the law of conservation of angular momentum and introduced rotational kinetic energy into conservation of energy. At this point, we have seen many of the principles associated with rotational motion, and we will see one last application in the next video.